Sergey Ivanov, Yaroslav Kurilev, and Marty Larsens. Manifold learning is one way of avoiding the curse of dimensionality in machine learning. So essentially, if you don't have any other distributional assumptions, most generic tasks like understanding the sample complexity or computational complexity associated with computations is going to be exponential in the intrinsic dimension, and this is often not tenable. So we make different kinds of assumptions, such as sparsity, or in our case, we'll talk about assuming that the data lies in the vicinity of a low-dimensional manifold. So this is called the manifold hypothesis. And if this hypothesis is true, we say that the manifold hypothesis holds. So in this talk, I'll first talk about one instance where this is very reasonable. It comes from CryoEM. Then I'll talk about some work on testing the manifold hypothesis, and then talk about fitting a putative manifold under a generative model. So why should measurements lie near a manifold? So if you take, for example, the case of CryoEM, here what happens is you have a large number of isometric large protein molecules embedded in a thin layer of ice. Then you shine an electron beam and you measure the shadow on a screen behind. And what you see are these shadows of randomly oriented molecules. And from these noisy shadows, we hope to understand the structure of these the three-dimensional structure of these molecules. So this can be viewed as measuring the line integral of some sort of electron density through the large protein. So it's if you think of these proteins as functions from a ball to the reals measuring the electron density, then the way rotations act on these is, of course, by spatially rotating the molecules, but viewing them as functions, these are functions in, let's say, L2 of the ball. So there is also an action of SO3, the rotation group, on these functions. And that is the thing that one needs to understand if one wants to reconstruct the the three-dimensional structure of a molecule from these shadows. So all of this gets approximated because when you take these pictures, there are pixels and so on. So it's not the entire picture that you get, but you get some sampled version. But it's a very high-dimensional sample if you have even 200 by 200 images. So you can view this as some sort of extremely high-dimensional space where you have vectors, and these vectors are not arbitrary. Rather, they are under the action of the rotation group. So this rotation group is only a three-dimensional group. It's acting on the rotation of three-dimensional space, but it is now acting on the space of images, which is a very high-dimensional space. So you have this orbit of SO3 on a which is a three-dimensional Lie group on a very high-dimensional space. And assuming the molecule is generic, we believe that the orbit would be a set that is diffeomorphic to SO3 and not it would not have other special structures. Like, for example, if you have a molecule that has icosahedral symmetries, then you can rotate it by some small amount and you will get exactly the same molecule. And this actually happens for the cases of viruses. But we are talking about the generic case. So here are two images. These are actual images from some a virus called HK97, which attacks Escherichia coli. So these pictures are obtained from Peter Doerschuk at Cornell. So here is the toy picture. You have this manifold, like a donut, surface of a donut embedded in some high-dimensional space. You have a generative model where you pick a random point in the manifold, add Gaussian noise, pick a random point in the manifold, add Gaussian noise, and so on. And from this, you would like to figure out what the manifold is from these noisy samples. So now I'll take a slight detour and talk about even testing the manifold hypothesis. So how can we test the manifold hypothesis, and how many samples do we need to perform this test? So answers of these questions are provided in work with Pfefferman and Mitter. It appeared in 2016. So we need to place some restrictions on the manifolds we're looking at, otherwise this is not a feasible task. So the restrictions we'll apply are that they have no boundary, they are d-dimensional, twice differentiable. So I'll explain this in the next slide. And then the reach of these manifolds is at least tau, and that the d-dimensional Hausdorff measure, which is basically the d-dimensional volume, is at most V. So what does this mean? It means that it has no boundary, and C2 means that for every point on the manifold, there is an epsilon greater than 0, such that if this is your manifold, then if you take an epsilon ball, then this is locally the graph of a function from the tangent space to the manifold to the normal space. So this intersection of the ball with this is the graph of a function from a domain to the range. This is not necessarily true globally. For example, if you take a circle, it's not the graph of a function because you have two images for every point in a certain set. But locally, we assume this is the case. And this is what reach means. Reach is basically the largest distance you can travel away from the manifold while preserving the unique projection property. So here, for example, I can go all the way till somewhere here, before which I have two nearest points on the manifold to the data point. Here, I can only travel this far because already I have two nearest points on the manifold. So this has small reach, whereas this has large reach. So the reach also incorporates some global aspects. So for example, if I have two parallel lines, these individually have zero curvature, but their reach is half of the distance between the two. The reason is that if I take a point that is halfway between the two lines, there are two nearest points, although these two nearest points lie on the respective lines, not on the same line. Yes. And Hausdorff measure is the most natural volume measure you would imagine. It has a simple definition in terms of taking limiting volumes of tubes and dividing by the volumes of the cross sections, but I won't go into that. So what we showed was that if you have if you're interested in the following question, there is data drawn from a ball in some high dimensional Euclidean space, which can even be a separable Hilbert space. But let's suppose it's some Rn for very large n, and you want to know does this data that you're drawing IID from a distribution correspond to a manifold that has dimension d, volume at most v, reach at least tau, then you can answer this question using a number of samples that does not depend on the ambient space, but only depends on d, v, tau and some error parameters epsilon and delta. So this delta is a confidence and epsilon is the squared distance that you are requiring. So note that this loss function is in terms of the underlying distribution. It's got nothing to do with the data. So it's not the empirical loss that we are asking to be small. We are asking that the true loss should be small, and yet the number of samples you need does not depend on the ambient dimension. Yeah. Class. Yeah, so that is a decision question we are interested in. So I'm saying with probability greater or equal to 1 minus epsilon, with 1 minus delta. Yeah, with respect to the samples, yeah. Yeah, so this was just what I just said. So the sample complexity only depends on intrinsic dimension, volume and reach, although these are all embedded manifolds in some high dimensional space. So what crucially matters here is that we are talking about the unit Euclidean ball, and it turns out that there are these loss functions that are basically both Lipschitz and have small VC dimension in the right sense, and together these two properties lead to a complete independence of the ambient dimension. So the technical thing goes through actually approximating these manifolds as point clouds, and then saying that the Hausdorff distance to one of these manifolds is actually pretty much the Hausdorff distance to one of these point clouds. And the point clouds, in fact, are a more rich function class in the sense that there are manifolds every point cloud does not have a nearby manifold, but every manifold has a nearby point cloud. So you basically prove a generalization bound for this larger class of k-means, and that does the job up to approximation. The key point is that the manifolds of this class have small covering numbers, and so that is what gives the answer. So this also now leads to the following algorithmic question. Given n points in the unit ball, is there a manifold of the class of interest such that the empirical squared loss is small? Here C is some constant depending only on D. And this, we had a longer answer to this, but it was also that yes, there is an algorithm that will tell so. However, this algorithm is not very efficient. It is doubly exponential in the intrinsic dimension D. It has very weak dependence on the ambient dimension, essentially linear, because if you even want to read the points in the ambient space, you need n queries. Alternately, you could work in a model where given any two vectors, the inner product takes one unit of cost, and then actually you will get complete independence from the ambient dimension, because you will just take a small number of inner products and that will do your job. But by small I mean doubly exponential in D, but D is assumed to be very small. So like in the question of interest, D was 3. Yeah. Yeah. No, but the thing is, so here we are answering a decision question, right? So the landscape of that decision question is pretty complicated, because we are talking about these manifolds which are themselves. Yeah. Yeah. Mm-hmm. Mm-hmm. Yeah. Uh-huh. I see. Okay, the same with the same epsilon, it probably would work. Uh, huh, correct. But the variance can be bad, no? I mean, are you saying that are you suggesting a sketching algorithm for computing inner product? Uh, no, huh. Yeah, I don't know. I'll have to look at what the variance of the estimator is, but because let's say we want within epsilon precision, how many samples do you need? This will probably be additive or both. I don't know, maybe one or the other. Yeah, because the loss was the additive loss. So this is now I'm going to a different generative model. I just claiming that this had a solution, and you will see most of the ingredients of the solution in the solution of this question. So now we have a different model which is very close to the question of CryoEM. Namely, you have this low dimensional manifold, and you have data being drawn from it, and with Gaussian noise added, and there are some conditions involving the reach and the noise. So this D can be, I believe, weakened, but right for now, this is the ambient dimension D, this is the reach, and this is little dimension D. As you see, the sigma has to be pretty small for this condition to hold, but I believe this can be weakened. So basically, we are saying that you take this manifold, add a small amount of noise, and now can you reconstruct the manifold, right? In Hausdorff distance, and also give a good manifold. So when you say reconstruct the manifold, I don't just want an epsilon net of the manifold. I want you to give me a data structure from which I can recover a manifold with good reach and which is close in Hausdorff distance to the true manifold. So this is what past work said. So they actually didn't care so much about the high dimensional settings. So their bounds depend very badly on the extrinsic dimension. If you want to get to within epsilon, you need epsilon to the minus capital D number of samples, which of course if D is 40,000 is extremely large. And there is a bias, but this bias is, note that this bias is quadratic. So they have gone beyond just the noise magnitude, and they're getting the variance of this. So we also can get this variance, but the thing is we are only going to work with the intrinsic dimension, and there's going to be some polynomial dependence on capital D, so like in the Hausdorff distance. But basically, the number of samples is going to be inverse polynomial in sigma with little d in the exponent as opposed to capital D, and effectively the same bound on the Hausdorff distance. Further, we will give a bound on the reach that is show that it degrades, but not too badly. It degrades by a factor of d to the 7. Yeah, it could, I think. So this might sort of go from. So this is a worst case notion of curvature. You'd probably get some average case notion of curvature from that. So it's possible that you get different results. Yeah. Yeah, I mean it makes sense in some situations to look at LP curvatures. So because then it's a different average. So now let me just go to the board and tell you. So here the algorithm is going to be you have this manifold, and you have these data samples which are IID Gaussians from the manifold. We are going to first compute approximate tangent spaces locally. So we're going to take these balls whose radii are r. I'll tell you what r is in a minute. But so how do we do it? So think of this as the manifold. Let's say yeah, okay, I'm sorry for this picture. I'm going to take the board board as the manifold, and we have data that is slightly above or slightly below it. I just want more than one dimension. That's why I'm doing this. So so now the way it's going to work is you choose one data point that's pretty far off, up close to r away from this point. This is a data sample, and then you pick another vector that is approximately orthogonal to this, and also a data point. So this is also slightly above or slightly below this, but they're approximately orthogonal. That's the key point. And now you take the linear span of this, it's going to be pretty close to being the board here. And the reason for that is this orthogonality or approximate orthogonality leads to some stability. If you didn't have this stability, what would happen? You would get one vector, then you might get another vector somewhere here that is really close within epsilon of this, but this could rotate all around. So when you take the linear span, you're going to get something very unstable. So this is just for stability. And one can show that if you do this d times, you get a basis that leads to something that is a disk that is within, so a disk like this that is within some delta Hausdorff distance of the intersection of the manifold with the ball. So that is, so this is just a, a near orthonormal basis. Good reach. Not ending? Yeah, I just didn't want to deal with boundaries, but so we are going to try to make the distance from x. So I don't know if this has all the details, but yeah. So okay. So here, we are going to look at we are going to try to make x and x prime to be close to 1 in length. So having things close together is not such an issue. I think the issue, of course, Gaussian errors mean that eventually, if you take too many samples, you start having large deviation, errors, and you don't want to have that. So you don't take too many samples. And one of the assumptions was that the density is log Lipschitz. So that takes care of the fact that you don't have to take too many samples. So yeah, so this is saying that these lengths are close to 1, and then the angle is given by the inner product. Yeah. So this is the lemma which says that the Hausdorff distance between the disk you get via this algorithm and the intersection of the ball with the manifold is actually close to 0. It's less than d delta. So now what we are going to do is we are going to patch up these disks. So what we have done is that we have taken this manifold and we have gotten lots of approximate tangent spaces. but now we want to patch these together in some nice way into a single manifold. So incidentally, this manifold is hidden. We only know the data samples, but from the data samples, we have managed to construct some good approximations to tangent spaces. So how do we patch these together? So there are two objects of importance here. So before I go into that, I'll talk about a data cleaning procedure that takes us from sigma Hausdorff distance to sigma squared Hausdorff distance. So once you've found these disks, you have all this data that is essentially like they're not from the disks, right? The thing is from the manifold, but if you have a disk of radius square root sigma and your reach is 1, then the reach condition ensures that the displacement here is sigma roughly, because it gets squared. So you know that this error is roughly sigma. That is also the error from the that is also the amount of error from the random samples. Now what you do is you do a function approximation for this unknown manifold using patches of length sigma. Instead of square root sigma, you go to sigma. So when you do that, you basically average. So it's a simple averaging thing, but it's not a flat thing you're averaging. So what will happen is that if at a scale of sigma, the quadratic term will contribute a sigma squared to you, and the average of these data samples will be very close to the average of the tangent at this point, one of these central points, and that for linear things, when you average, you continue to get linear things in this model. So what will basically contribute is this thing and the standard deviation from the samples, but then if you take enough samples, you can get that contribution down. So you end up getting a bias of sigma squared. So what you'll get is, for this patch of sigma, you'll get one point which is within sigma squared of the true manifold. And then you take another patch, get another sample of that is within sigma squared of the manifold, and so on. Okay, so that way you get lots of points within sigma squared of the manifold, and now we have to build the manifold using these points. Okay, so these just at scale sigma give Hausdorff distance sigma squared. So there is some additional technicalities here. Basically, the patches, the number of patches that interact on a d-dimensional manifold is roughly exponential in d. If the patches have large overlaps, then they can be as much as d raised to d. As in our case, actually the distance between the patches is 1 by d on a scale of 1. So what that means is that you have lots of these patches interacting, and that is going to create some dependencies that are exponential in nature, because there are exponentially many such balls that intersect together. So if you don't want that, then there is some workaround involving carefully chosen partitions of unity, and we get a polynomial dependence using that. But that is a detail that I won't go into here. So I'll just go into the core algorithm. So the core algorithm is to take these balls and take these disks and these balls, and now we construct what is known as a fiber bundle over this ball. What do? You take a point here, and you take the ortho complement of this disk, which is a d-dimensional disk, and this is going to be n minus d-dimensional disk, a affine plane. Similarly here, you take a n minus d-dimensional affine plane through it, and for every point, this is a completely flat vector bundle. Every point has this affine plane through it. Now you assign not just that plane, but the projection onto this subspace, which we call pi I for the ith disk. So pi I is the projection onto this kind of a plane through the origin, and this plane is n minus d dimensional, and these pi I are now indexed by I, where this is the ith ball. Secondly, we'll have a function, a vector valued function fi, which given a point takes the projection of this point onto the plane, the d-dimensional plane, and takes the vector corresponding to that in the opposite direction. So these are outward going vectors. So this is, you have pi I and you also have fi. Okay, so you have these two objects. Then you have that partition of unity I skipped over, which allows you to patch together over unions of balls fi and pi I. What is this? This is actually like a bump function. It has the property that over each ball you have a bump function. However, these things over a thin neighborhood of the disks, so these disks are very well aligned by virtue of their being almost tangent planes. So in these neighborhoods of disks, these summation phi I is approximately 1. Okay, so these are like bump functions defined on these neighborhoods of disks. They all add up approximately to 1 for all of them. Now you consider the two terms summation phi I, pi I, and you consider summation phi I, fi. Okay, so these are two objects. This is no longer a projection matrix because it's been mixing projection matrices with different projection planes. However, it's pretty close to a projection matrix because for non-zero phi I, these things are very well aligned. Okay, so what you do is you take the nearest projection matrix to this non-projection matrix. Okay, so this is a way of deriving a function which smoothly varies over these unions of balls, or at least over the unions of these slabs, and further has the property that it is always a projection matrix. Okay, nearest projection matrix is measured in Frobenius norm. Okay, so there is also a closed formula, but never mind that. So now what do we have? We have these projection matrices that are in the vicinity of the manifold varying smoothly. I'll draw the planes corresponding to some few of these points. And we also have the function f, which is obtained by merging these vector valued functions fi. So now you view the manifold as set of